Welcome back to BAS 120. Today we're going to talk about Chapter 5, the probability distribution, and how we can take probability and do some modeling of data and simulation. So first we're going to, some of the topics. First we're going to talk about some of the basic concepts of probability. We're going to define it and talk about some of the laws. Then we're going to talk about what a probability distribution is. Basically, how do we use these probabilities to help us forecast in business and help us do simulations and do some random sampling, our last topic, so that we can do Monte Carlo simulations, so that we can do some predictions to work to our advantage. So first, let's go over a few terms. Probability is the likelihood of an event or an outcome occurs. It's normally represented from 0 to 1. Sometimes people multiply by 100 and talk about from 0 to 100%. You've probably heard, the probability of me rolling a strike in bowling is 40% or 0.4. Normally they put it in a number between 0 and 1. Sometimes they convert it to a percent. An experiment is a process that results in an outcome. An outcome is a reserved result. Sample space is a collection of all the possible outcomes. An event is a collection of one or more outcomes from a sample space. So let's give an example of this. Let's talk about getting a 6 on one roll of the dice. So the probability would be the likelihood of getting a 6. Well, I think most of us intuitively know that's 1 out of 6, 1/6. The experiment would be the process of actually rolling the dice. The outcome would be what we observe. The sample space would be all the possible outcomes, which would be 1, 2, 3, 4, 5, 6. And the event would be what defines success. The event would be getting a 6. Now, probability can be, if you think of it as a range, if we're close to 1, it's almost certain. If it's almost 0, it's almost impossible. And we have areas here where the chance, like the odds of rolling that 6 is not very likely, 1 in 6. Flipping a coin, pretty even, 50-50. And then we have some events that are very likely to happen. But we can put these on a continuum, and this becomes very helpful later on when we say, well, if an event is very almost impossible to happen, we might come to some different conclusions. We're going to get much like a court would when they're deciding guilt or innocence. In statistics, nothing is ever totally impossible. Most things aren't totally impossible, and most things aren't totally certain. So here's a simple continuum of how probability works. Now, we've got a couple definitions of probability. We've got what's called the classical definition, which simply says the total successful outcome. So in our dice rolling of rolling a 6, there's only one successful outcome. Only one way to roll a 6, we roll a 6. And we divide that by the total possible outcomes. There's 6 ways the dice can come out. There's only one way we're a winner or successful, so the odds or the probability is 1 in 6. Now, why don't we use this all the time? Well, there's some limitations. Sometimes we don't know all the possible outcomes. So let's talk about the next way to define it, which is called relative frequency. Let's say we're talking about repair times at a car garage or a computer outfit, right? We don't know all the possible outcomes, so oftentimes we'll have to take a sample or a relative frequency. We would say, again, we use the same definition, total successful outcomes divided by total possible, but we're just estimating the total possible based on a sample. We've done repair times for the last months. 40% of them are done in less than 2 days. Therefore, the probability of you getting your computer repaired in 2 days is 40%. We take a relative frequency. We take empirical data, normally a sample or our past history, and we say based on past history, we repair 40% of the computers in 2 days or less. That's how we come up with the probability. We don't know every single computer. Now, the limitations of this is, if you think about it, it's only as good as our data is. And there's nothing that says the probability may not change. Maybe we hire more staff, so we start repairing things quicker. Maybe our staff gets better trained or gets more used to it, so they get faster. So relative frequency is often used because very rarely do we know, are we lucky enough to have a dice roll where we know every outcome, but it has its limitations too. Now, the third type and final type of probability is what's called a subjective probability. So, if we want to know the Super Bowl outcome or the stock market growth, we don't have any experiments to go. We don't have any we don't have any data to analyze. We don't have any empirical data. We don't know. We certainly don't know all the possible outcomes. So we go and we ask experts, and the experts do the same thing. They subjectively decide what is the total success divided by the possible outcomes. And again, it's useful, and it's often used if we don't have data. But again, its limitation is it's only as good as the experts we have. And I think anyone who follows the stock market or follows sports or any of these things, experts certainly differ. So just to summarize the probability definitions, they're all based on this total successes divided by total possible outcomes. It's just sometimes we know more information in certain situations. So the classical definition is when we know what the outcomes are. We know if we roll a dice, the outcomes are 1 to 6. Limitations is we often don't know what all the outcomes are. Relative is based on empirical data. Again, its limitations is it's only as good as our data. And then the subjective is where we have no empirical data. We don't know all the outcomes, so we go ask experts for their opinion. And again, it's only as good as the experts. So those are the different types of probability and the different definitions. So let's talk about what an event is and the complement some of the probability laws. So rule number 1 is the probability of an event is the sum of the probability of the outcomes that comprise the event. So this sounds complicated, but it's, if we're rolling the dice, probability of getting a 5 or a 6 is equal to the probability of getting a 5 plus the probability of getting 6. It's basically the way we're defining success is we're adding up all the possible outcomes that define success. So if you say success is getting a 5 or a 6, then we add the probability of a 5 plus the probability of 6. So in this case, there's one way to get a 5 and there's one way to get a 6. So we'd add those together and we'd say the probability of getting a 5 or a 6 is 2 6. Rule number 2 is, what the complement of the event, i.e. not rolling a 5 or a 6, is just 1 minus the probability of getting a 5 or a 6. Now this sounds relatively obvious and simple, but we use this a lot. It's one of these rules that we're going to use a lot. So the probability of getting a 5 or a 6 is 2 6. Probability of not getting a 5 or a 6 is just 1 minus the probability of getting the 5 or the 6, or 2 6, which gives us 4 6. Now let's talk about a concept of mutually exclusive. So mutually exclusive are two events that have no outcomes in common. So if we think of a coin toss here, I can't flip a coin and get a heads and a tails. I get one or the other. They have no common outcomes, right? I have to get one or the other. Now, if the events are mutually exclusive, then the probability of A or B is just the addition of the probability of A or the probability of B. So let's think of it. What's the probability of us getting a heads or a tails? Well, it's the probability of getting a heads, which is 1/2, plus the probability of getting a tail, which is 1/2. So the probability of getting a heads or a tail is 1, which hopefully is making sense because we have to have one of those two. We're 100% sure we're going to get either a heads or a tail when we flip a coin. Mutually exclusive, sum of rolling 2 dice, right? So probability of odds or a 6. Are they mutually exclusive? Yeah, 6 is not an odd number. So the probability of getting an odd number when I roll 2 dice and sum them up. So here's the distribution. There's one way to get a 2. There's 2 ways I can get a 3. 3 ways I can get a 4. 36 total possible outcomes. So over here on the left, so the probability of getting a 2 is 1/36. A 3 is 2/36 or 1/18. A 4 is 3/36, 4/36, and all the way up to the probability of a 7 is 6/36. So the probability of getting an odd sum or a 6. The first question we have to ask ourselves is, are these mutually exclusive events? And yes, they are. I cannot get an odd. I either get an odd or I can't get both an odd and a 6. So the probability of getting, so I can use our rule number 2 where I add the probabilities together. So the probability of odd is 1836 plus the probability of 6, which is 536. So the probability of getting an odd or a 6 when I roll 2 dice and sum them up is 23 out of 36. Now let's say they're not mutually exclusive events. So let's give an example here. The probability of a student likes math or science. Let's say the probability of so let's say 60% of our students like science and 55% of our students like math. Well, we can't use that rule we used for mutually exclusive events. We can't add them together, because if we add them together, we get 115%, and the probability hopefully can't be more than 100%. So we have to do something here, right? So what you might think about is, well, wait a minute, we're double counting all those students that like both, right? 60% of the students like science, 55% like math. Somehow we got to exclude all those students that like both. So that's what we do. We say 60% of the students like math, 55% of the students like science. Well, how many of them like both? Well, we take our data and we say 40% of them like both. So that we make sure we don't double count those folks that like both, we subtract it from the total of the first two. So that's how we do non-mutually exclusive events. So if we wanted to calculate the probability of a student's liking math or science, we would take the probability of the ones that like science plus the probability of the ones that like math and subtract from that the ones that like both. And that's the rule number 4. The probability of A or B for non-mutually exclusive events is the probability of A plus the probability of B minus the probability of A and B. So we're basically subtracting those folks that like both math and science. So for rolling the dice, the example would be, what's the probability of an odd number or a 7? Well, these aren't mutually exclusive because 7 is both an odd number and, of course, it's a 7. So we're going to have to use the non-mutually exclusive equation. Probability of odd is 1836. Probability of a 7 is 636. Minus the probability of a 7 and an odd is 636. So we get 1836, which is 1/2. Which sort of makes sense because I'm either going to roll an odd or an even number, and since 7 is already an odd number, having an odd or a 7 doesn't add anything to our probability because it's already an odd number. So let's talk a little bit about conditional probability. So this is very valuable here. So a conditional probability is where we know a prior outcome or a condition. So if I said to you, is my team going to win? We might say, well, there's a 50% chance of the big game, a 50% chance our team wins. But then if I tell you, oh, the star player can't play, that might change the probability. So same thing in card games, poker. Each round you bet a different amount. Well, what if I'm dealt 2 aces? If I say, what's the probability of me having a winning hand? And you say, 25%, let's say. And I say, oh, no, wait a minute, you were dealt 2 aces. Well, that's going to change your probability. The probability changes based on a condition. So in business, it might be, what's the probability that someone out there is going to buy a new car? Well, is that, what if I then told you, well, no, the person's car is 8 years old? Well, their probability is their existing car ages, the probability of them buying a new car goes way up. And you can think about some of the implications here. Maybe I segment my market based on these conditional probabilities to better utilize my advertising dollars. Same thing with buying gutter guards, all sorts of purchases. Conditional probability is the simple concept of I know some additional information. It's based on a condition. So there's lots of examples in the book, but I'll give you a very simple one here. Let's go back to this purchasing a new car in the last year. Let's say we did a survey of all our car dealership customers, and we found that 275 purchased a new car last year. Of those, 25, the age of their existing car was either less than a year, 1 to 5 years, or over 5 years. And then 600 people did not purchase a new car. So we did a total survey of 875 people. So if we said event A was the purchase of a new car in the last year, we know that's 275 purchased new cars out of 875. So about 31% of the people purchased a new car. If we said event B is how many people have existing cars whose age is over 5 years. Well, we know there's 350 cars over 5 years out of our total sample of 875. So 40% of the cars out there, of the customers out there, have cars current age over 5 years. Well, the probability of A and B, right, i.e. they purchased a new car and their existing car is over 5 years, is going to be 200 divided by our 875, or about 22%. Now, here's where the conditional probability is. What is the probability that they purchased a new car in the last year, event A, given that they have a car over 5 years old? Well, that would be, now all we're worried about is, right, because we already know we're only worried about the folks that have a car over 5 years. So that's 200 divided by our 350, which is 57%. So if you go to the book and see the formula, the official formula for conditional probability is the probability of A and B divided by the probability of B. So that would be the probability of A and B divided by the probability of B. So all of a sudden, rather than just the probability that our customer buys a new car is only 31%. But if you tell me they have an existing car over 5 years old, that 31% jumps to 57%. So lots of marketing, advertising implications, and there's lots of examples in the rest of the videos where we go through all sorts of examples on conditional probability. There is the formula for conditional probability. The probability of B, event B, given A, is the probability of A and B divided by the probability of A. Now, there's all sorts of fun things on discussion boards. There's a neat Monty Hall problem where, I don't know if you've seen the Let's Make a Deal show, where you deal from pick from 3 doors, and you might know certain information and the probabilities change based on the condition. If you knew what one of the doors was, that would change your probabilities. Let's talk about the multiplication law. So the multiplication law is the probability of 2 events, given that the 2 events are independent, probability of A and B, you can multiply the 2 together. So let's say the probability that I win the lottery week 1 and I win the lottery week 2. Well, let's say week 1 there were 100,000 people that entered the lottery, so my odds of winning were 1 in 100,000. Week 2, my odds of winning was 1 in 75,000, because apparently fewer people entered that lottery that week. The probability that I win them both is the multiplication of the 2 of them. 1 over 100,000 times 1 over 75,000. So I get 1 in 7.5 billion, which should sort of make sense that the odds of me winning the lottery 2 weeks in a row is pretty astronomical. Another example, the multiplication rule. Let's assume I'm a 90% foul shooter, i.e. I make 90% of my foul shots. What's the probability that I make 5 in a row? Well, again, it's the multiplication. Event A, 0.9 times 0.9 times 0.9. So about 59%. Or some people would say it's 9 to the 5th power. That's the symbol for in Excel for raising to the 5th power. You can do the same thing. The probability that I make 25 in a row or I make 10 in a row is 0.9 raised to the 10th, which is about 72%. That I make 25 in a row. So the probability that I make 25 in a row is 0.9 raised to the 25th, which is only about 7%. That's the multiplication rule. Last thing is, what is independent events? So two events are independent if the formal definition, the probability of A given B is equal to the probability of A. So if you think about that formula, what it's really saying is B has no effect, no influence whatsoever on the probability of A. The probability of event A is the same no matter what happens in event B. They're independent of each other. There's no influence. The fact that B has happened does not change or influence the probability of event A. So some examples are flipping a coin, right? The fact that I got a heads on the first one has no influence on the next flip. Rolling a dice. Foul shots in theory. So, you can argue, well, if you're hot if you make the first one, and people say the same thing sometimes with rolling. But in theory, each one of these is an independent event. All right. Next video, we're going to break this into two. We're going to walk through the concept of a probability distribution, where we'll talk about a bunch of stuff here. So that'll be in part 2. Thanks.